Okay, let me just go over the calendar real quick here. I'm going to be pushing the test one day back. So instead of Thursday, we're going to have an extra day of review, and the test will be on Friday. Okay, test is on Friday. I have your 5.2, 5.5 quiz graded. I'm going to enter that in this afternoon, and I'll get that back to you tomorrow. Okay, 30-point quiz. Most of us did okay on it, but hopefully we can spend some time either tomorrow or Thursday just reviewing, going over some of those problems. I also have your Chapter 4 calculator test graded. I'll hand that back to you tomorrow as well. There's no assessments next week, so the recovery for Chapter 4 will be next Friday. For anyone who needs to recover or who wants to recover their test grade up to 79. You'll come in, you'll do corrections sometime next week, and then ask questions if you have any, and then take that recovery test next Friday up to 79. Okay. I'm going to have some help sessions this week for the Chapter 5 and 6 tests. So tomorrow afternoon, 3:40, Thursday morning, 7:30, and Friday morning, 7:15. Okay. I'll send out a reminder this afternoon so you can kind of see the schedule, and also update my website as well. So you can, if you're going there to watch videos or going there to pull any keys, I will you'll see those dates listed. Okay. And then all these help sessions, if you don't attend them, but you still want to watch the videos, I'll record all of them. Okay, if you want to check those out. And I'll also send a Teams link if you want to join in during that time that I hold the help session. Okay, so in your packets, we have one more kind of new thing to go over. Not really new, it's more really just an additional item, which is finding the domain of domains for differential equations. But as we go through this, we're going to also be reviewing a lot of stuff that we need for the test. Okay. And just to let you know, I put 4 test reviews in this packet. And so starting on page 3, I have test review 1, and test review 2, test review 3, test review 4, and then I put the key for all the worksheets near the back. So if you want to get a head start in terms of like working through those problems leading up to that Friday test, you're welcome to do that. Hopefully that resource will be helpful. All right, so let me just read through the notes here. So finding domain. Domain of a solution to a differential equation is the largest open interval containing the initial value, okay, given for which both the differential equation and the solution are defined. This is called the maximum interval of existence. Okay, so first thing we do is we're going to solve the differential equation, just like how we've been focused on a lot of last week, and then we're going to graduate from the general solution to the specific solution. Right? Once we have that general solution, we have that plus C or that times C, and then we're going to update that general to a specific solution and solve for that C value. Okay. We're going to find the initial domain of the specific solution. We're going to further restrict the domain by finding the domain of differential equation. Be sure the initial condition is included in the domain. We'll graph the solution, use slope fields to help determine and confirm the domain. We'll incorporate the restrictions to find the final domain. And this is an important note here that we'll go through as we work through example 1. Domain can only be one open interval that includes the initial value. So if there's any break, we're not going to include that second part. It's only going to be one branch. It's never going to be, 3 to 5 and then 5 to infinity. If there is any break in the graph, we're going to cut that break. We're going to not include the other part that doesn't include the ordered pair with the initial value. Okay, so I'm going to be working through example 1 on a separate sheet because I want to make sure that I have enough room. I did not quite give us enough room for all of number 1, so If you want to put on a separate sheet, you're welcome to as well, but just know that I did not provide a whole lot of room to do the example one. So let's look at example one here. It says given dy dx equals 1 over x squared y, and y of -1 equals -2. That's our initial order pair. That's going to be eventually what we're going to use to solve for c. It says find the particular solution. So we're going to solve the differential equation. So just like how we've been doing ever since we introduced this topic, right? Cross multiply, separate the variables, and then identify the appropriate integral rule for each side, take the antiderivative, plus c shows up, and then we go from there. Okay, so cross product. Again, it may not separate the variables, but it will get your dy dx's in their right slots. Okay, so cross multiplying, I have my dy dx's. Those are locked in place. I don't want to be moving them anymore. But now we got to take a step back and say, okay, is there anything else that we need to move? Is there anything that's out of place? X squared. So what do we do? Okay, divide. Okay, so it's going to be in the denominator, which is where it is going to be initially. Okay, if we have to move it, we can do that later. But right now, we'll leave it in the denominator. Okay, so this is what I have here. So before we jump into the rule, let's just look at the problem and identify what rule we're going to target. Okay, what rule do we want to use on the left side? Okay, good, power rule. Okay, we'll do that in a second. How about the 1 over x squared? Right. Okay, good. It is not what? It's not. Well, okay. And it's okay, good. It's not natural log. Yeah, I just want to make sure that we understand that just because we see a variable in the denominator, we're not going to always assume that it's natural log, right? We have a very specific way of telling a natural log problem. If the variable, if it's u to the first power or if it's x to the first power, that's the only time you use natural log in the denominator, right? If it's any other power, you got to take that additional step, got to move it up and go through power rule. So I don't want us to just assume that, oh, variable in the denominator, I'm going to do natural log, right? It's very, very specific. It's got to be that first, it's got to be degree 1 showing that exponent has to be 1 if I want to do power, if I want to do natural log for this problem. Okay, so not a natural log problem. We're going to bring it up to the top. Then we're going to do power rule for both sides. Okay, good. All right, left side, power rule, y becomes good, 1/2 y squared. Right side, x to the -2 becomes and don't forget plus c. Okay, now the calculus portion is done. We've gotten everything up to the function level, but I'm still going to do a little bit of cleanup before I call it the general equation. It says to just find a particular solution, but we always want to think in terms of, okay, there's really a pre-step to this, right? Particular solution, we always have to get to the general first before we can get to the particular. So I'm going to do some cleanup here. I know I can't get y by itself, but I can get y squared by itself. And that is a relatively clean spot for us to call it a general solution because the particular solution won't be too hard after that. So I'm going to clean up the right side a little bit here before taking care of that divided by 2. So I push that x down to the denominator. And then there's one more thing I can do. I can multiply both sides by 2 to get that left side a little bit more cleaned up. Distribute the 2 through. Distribute the 2 through, I get -2 over x. And then 2 times c, I'm still going to leave it as plus c. Okay, I'm going to just call this the general solution here, or general equation. Okay, good so far? Now let's involve the order pair. The order pair is going to help us get to that c value. So -1, I'll insert -1 in for x. I'll insert -2 in for y. Right, c equals 4 minus 2, right? C equals 2, right? All right, so now that I have my c value, I'm going to go back to my general equation, and I'm just going to make that substitution. All right, so now that I have my c value resolved, I'm going to get that y squared down to in terms of y. So what can I do? Square root. What's going to happen, though, on the right side? Good. 2 solutions, but we only want 1. How do I choose between the positive or the negative square root? The y value is negative. So good. So I want to choose the negative square root. Oops, sorry, plus 2, not c. Okay, this is now our particular solution. Okay, so any questions so far? I'll leave that up there for a second. All right, no issues. Okay, let's go back to this page here. Okay, so we have A. I'm just going to copy that down here. We have our particular solution. Okay, we're going to now work towards finding the domain, but to get to the domain, we're going to build the graph first. Okay, so we're going to spend the time here just to review how to create a slope field. So look at your differential equation and look at your slope field. What do you notice about if I try to insert any order pair with a y value of 0, what's going to happen? Undefined, right? So undefined means I'm going to leave that space blank. So right, if I try to plug in -3, 0, -2, 0, -1, 0, it's all going to end up giving me undefined because that derivative all produce zeros in the denominator. We know that's not going to work. Okay, so we can ignore basically anything on the x-axis. What about the y-axis when x is 0? Also undefined. Okay, so we know that those are going to be kind of breaking points for our graph. Okay, so just keep that in mind in this case. So it's still quite a few points, but we're just going to do maybe 2 of these quadrants, and then I'll fill out the rest. You can copy that down. But this is how we do it, right? We identify any order pair that we want to target. So let's say this is -3, 2. -3 is the x value, 2 is the y value. You're going to insert that -3, 2 into your differential equation, and then you're going to get a number in return. Whatever number you get in return, you're going to translate that number into a slope, and then just do a short line segment through that order pair. So if I enter in 3 squared, 3 in for x, I get 3 squared, which is 9. 9 times 2 is 18. That's positive, but it's 1 over 18, so that's a very, very gradual slope. It's almost flat. So you're just going to do a positive slope, but then a very gradual positive slope. Okay. This next order pair is negative 2, 2. I get 1 over 4 times 2. That's 1/8. That's a little bit steeper, but it's still going to be very gradual. Okay, you're really not going to be graded in terms of how accurate your segment is. As long as you can do a positive and negative and just try to adjust in terms of the steepness, that's good enough. All right, so here, this is negative 1, 2. I get 1 over 2. That's 1/2. It's a little bit steeper. Okay. And then here, I'll fill this in as well. This is negative 1, 1. Negative 1, 1 will just be 1 over 1. This will be the steepest out of all these ones here. This is negative 2, 1, so 1/4. And then 1/9. Okay, let me go down to the third quadrant here. This is negative 1, negative 1. Now, everything here, because the y's are all negative, this is all going to end up being negative slopes here. So negative 1. Okay, just going to go down the line here. Any questions on how to create these slope fields or slope segments? Okay, I'm going to just fill out the right side. You can just copy it down here. Okay, so the slope field kind of helps us determine how the direction of the graph is going to look. We also have the specific solutions, so we're going to kind of pair those things up and try to sketch the graph, because we need the graph showing in front of us, and we can just read the graph and then from there find the domain. Okay, so just to have a basic idea as to what this graph looks like, a square root kind of has a starting point and kind of moves up, but this is negative square root, so it's going to kind of have this shape to it, right? It's going to kind of have this shape to it. So we're going to try to sketch that graph through the point, okay? Something that looks like this. Now, we know that whatever graph we create has to go through your order pair. So this is your anchor point, okay? Let's plot that point first. Negative 1, negative 2. Okay. We know there is an asymptote here, or not, or maybe not an asymptote, but we know that there's a break here, right? Nothing here and nothing here, but we know the graph is going to kind of have this flow to it. So I'm just going to sketch the graph to the best of my ability. And I know that my graph is going to have to come to this line, but it can't cross it because we know that the slope doesn't exist on the y-axis. So we're essentially looking at this graph here. Right? We make it go through the point. We kind of follow the slope field. We kind of have an idea that it's what the graph is going to look like. The slope field also helps a little bit. And we also know where it stops, because it can't jump over the asymptote, because we know the slope doesn't exist there. So now you may look at it and say, well, the graph can continue on the other side, right? Well, maybe for the graph it can, but we're only concerned about the branch that the open interval that includes the initial value. So as soon as it hits a break, you're going to stop. We don't care about anything else. We just care about the domain for this branch here. Okay. So now, based off of what you see there, what's the domain? Right. The furthest left x value that the graph goes is negative infinity. The furthest right it goes is 0, because 0 is the y-axis. And what do we put at 0? Bracket or parentheses? Parentheses, right? It doesn't hit, it actually doesn't hit that point. It's open circle, so parentheses. Okay, any questions there? Yeah. Right, we know it's in that quadrant because the order pair tells us. Right, so wherever the order pair is, that's where the graph has to live. So it may be living in other places because based off of these slope fields, but we only care about what is part of our order pair. Okay. Okay, it's good to double check that your X value of your order pair lives in your domain. It does, right? -1 does fall between infinity and 0, and that's important to make sure, right? Be sure the initial condition is included in the domain. Good. Now, part C. Part C says find the equation of the tangent line through -1, -2, and then use it to approximate y of -1.1. So C and D is review from first semester, but I'll go through it fully and make sure that you're comfortable with these first semester topics that's showing up. So I'll put this on a separate sheet here just to have more room. And I'm also going to copy down the differential equation because we're going to be using that a lot. Okay, so here it is. Here's part C. Find the equation of tangent line through -1, -2. We're going to be using the differential equation. Now, tangent line equation for first semester, what information do we need to create tangent line equation? Point and slope. Okay, good. We have the point because that's what they give us. The slope is going to come from your dy dx. I know it looks a little bit different than your f prime from first semester, but it does the same thing as f prime. Okay, this is your slope equation. As we were using with the slope field, right? Slope field, we use the derivative to help us get to the slope. So that this is the slope equation. So this is also the derivative, right? And this is kind of like your f prime. Okay, maybe it's not quite a function, but it serves the same purpose as f prime. Remember how we're able to pull f primes? We used f prime to find slope. Same thing here. Your dy dx is basically your f prime. It looks a little bit different with this notation. There's a y involved, but I just want to help us make that connection that this is really not that different from first semester, right? Which is that we're able to take the integral that we didn't do from first semester, but it does the same thing as f prime. It finds the slope for you. So let's find the slope using our derivative. So I'm going to insert the order pair into the differential equation. I used this vertical bar to indicate that, okay, I have this derivative requires more than one x value. I can't just say y prime of -1. So I do this -1, -2 to indicate that I have more than one value that I'm going to insert into the derivative. Okay, what does that give us? Yeah, -1/2. So I have my order pair. I have my slope. And now point slope form. Do a little bit of cleanup. Now we have our tangent line equation. Okay, any questions here? So first semester topic, we're bringing that back here. Okay. Now part D says use it to approximate y of -1.1. Now part D is also a first semester topic, but this is maybe less familiar because we didn't spend a lot of time doing this. But this falls under the category of linear approximation. Okay, and I want to remind us about linear approximation. I know it sounds complicated, but you should really think of this as an easy thing, okay? All we're doing with linear approximation is we're just taking the tangent line equation, and we're just inserting this decimal value into the x. That's all we're doing, okay? We're not really even doing a whole lot. We're just plugging in. That's all we're doing. So there's not really anything. And once you get that tangent line equation, it should feel easy because you're just inserting, okay? So we're going to take our tangent line equation from part C. I'm going to do a little bit of rearranging, get that y by itself. So I'll subtract 2 to the other side. And all we're doing, once I get that y by itself, I'm going to take that decimal value that they provided for us. I'm just going to insert it into the x of my tangent line equation. That's all we're doing. So it feels like there should be more, but it really is just as simple as that, okay? And then make the calculator find the decimal value for you. Okay, any questions here? Okay, so let's look back at number 1 again, just to kind of talk about all the things that we did, because this type of problem is a very kind of a common and popular format for an AP exam, at least the ones that involve solving differential equations. Usually you're going to see a problem where you're going to solve a differential equation, like how we did for part A, create a slope field, but typically the slope field they ask you to create won't be as many points as we did here. Typically it's only 6 to 10 points, and usually it's somewhere closer to 6 than 10. And then you're going to sketch the graph, identify your domain, and then tangent line equation, pull the order pair, pull the slope from the differential equation, point slope form, and then linear approximation, take that decimal value they provide for you and insert it into the tangent line equation. Okay, any questions with number 1? Right, so we covered a whole lot of material just by going through number 1. It's a good review for us. We're going to skip number 2, and we're going to go to the next page. Go to page 3. We'll do a word problem involving the y equals ce to the kt. Does anybody still need this? All right, so page 3. Okay. Let me read the problem here. Oil is being pumped continuously from a certain oil well at a rate proportional to the amount of oil left in the well. So that's dy dt equals ky, proportional to the amount of oil. So anytime we see this y prime equals ky, we kind of know what's going to happen, right? Y prime equals ky. We can separate the variables and solve the differential equation, but it's always just going to turn into y equals ce to the kt. So if we knew that, we can skip the calculus involved and just jump directly to the general equation. So after you get to this point, there's really not any calculus left. We're just using order pairs and solving for C, solve for K. Okay, but really the calculus is already done just by going from here to here. Now, Y is the amount of oil left in the well, and then time T in terms of years. Initially, there were 1 million gallons of oil in the well. 6 years later, there's 500,000 gallons remaining. Write an equation for Y, the amount of oil remaining in the well at time T. Okay, so with these word problems, I like to organize information with order pairs. It just feels like I can, just feels more structured that way. So I'll treat T as my X, and I'll treat the oil, the Y. So variable T for the X and variable Y for the dependent. Now, let's create some order pairs here. Initially, there were 1 million gallons of oil. So what order pair can I create with that? Initially is time, T equals what? 0. Okay, so we know that year 0, or when we start the timer, or when we start counting, there's 1 million gallons at the beginning that oil is getting pumped. 6 years later, there's 500,000 remaining. Okay. So we create a second order pair, right? 6, 500,000. And this should be enough to get to our equation, because the first order pair will help us find C. Yes.
Would the C be like GT? I think it's really good.
Well, this is the general equation, and then we're going to update the C and the K value to finish the equation. Yeah. So this is partially finished, but we still have to find the C and K.
Right.
And then the second order pair will help us find the K value. So I'm going to insert 0 in for T and 1 million in for Y, and I can work backwards, solve for C here. K times 0 is 0, e to the 0 is 1, so my C is just 1 million. Okay. As soon as I have my C value, I'm going to update my equation, replace the C with 1 million. Use my second order pair to find the K. So 6 in for T and 500,000 in for Y. Okay, divide both sides by 1 million. We can get to that e to the 6k, and then we can decide what to do next. Okay, what does the left side reduce to be here? 1/2, 4.5. Okay, I'm interested in solving for k. I want to find a way to get that k to come down. So what can I involve here to bring that exponent down? Natural log, okay? Exponent comes down. Natural log of e goes to 1. Divide both sides by 6. And now we can write our particular solution because we have our C and K found. Okay, so there's my specific equation for part A. Okay, any questions with part A here?
What is K representing?
K is the constant that is building that relationship. It's the rate proportional to the amount of oil in the well. So it's that connecting piece that relates the two sides of the equation. So it's just a piece that we need to get to the particular equation. Okay, part B. Eventually, we're going to use this equation to predict certain scenarios happening in the future or for a particular time period. But for part B, let's see here. Part B says, at what rate is the amount of oil decreasing when there's 600,000 gallons of oil remaining? We know 600,000 refers to the Y value. Okay, but it says, at what rate is the amount of oil decreasing? Do we have a formula that tells us about the rate that the oil is changing? Yeah, good. The first one. This is the rate at which oil is being, the rate at which oil is, the amount of oil is changing in the oil well. So all we do, if we want to find dy dt, the rates, we just have to figure out the right side. Okay? We just found the K value, so all we need to do is to insert what we did from part A and then the 600,000 into the dy dt. Okay, make the calculator do the work for you there. This is a rate. This rate is in gallons per year. So we know that when there's only 600,000 gallons of oil remaining, the amount of oil is changing at a rate of 69,000 per year, or gallons per year. Okay, so part C is where we refer back to part A. It will no longer be profitable to pump oil when there are fewer than 50,000 gallons remaining. In order to not lose money, what time T should oil no longer be pumped from the well? Okay, so again, let's create order pair here. We're trying to solve for T. How long will it take before 50,000 gallons of oil remains? Because we know that's the time where we should stop. So we're going to involve part A. We have a specific equation. We can insert 50,000 in for Y and then work to solve for T. If we solve for T, we can figure out how long it takes, how many years it takes before the oil well goes down to this amount. Okay, just like before, we want to isolate the T, but let's divide both sides by 1,000,000 first. This ends up being a smaller value here. This is only 0.05. Again, I want to solve for T that is sitting up at in the exponent position. Take the what of both sides, natural log. That exponent is now free to come down to the base level. And we know natural log of v is just equal to 1, so that can go away. Okay, so final step, just divide whatever that decimal value is over. The calculator should give you t equals 25.932 years.
Why'd you multiply by natural log of e?
Because the natural log of e is the base, right? I took the natural log of both sides, so it ends up giving me natural log of e.
Yeah,
And
that,
when that exponent comes down, it comes down with that base, right?
oh, okay.
If I have natural log of a to the n, once that n comes down, I still have that natural log of a sitting there. So in this case, it's natural log of e to the exponent.
It's 1.5.
Okay, I'm used to just canceling the natural log of e.
Which is right. Which is fine. Yeah, you just cancel that out, which is 1. So. Okay, I'd like for us to do a little bit of part 2. Oh, sorry, number 2. For number 2, we'll skip the slow field. Let's just do part C. I just want to get that additional practice of solving differential equation. So for number 2, if you can look at the differential equation and separate the variables, and let's do part C. Just part C. All right. So we're going to solve the differential equation or find a particular solution. But we know that if it's asking you to find a particular solution, you're always getting to the general first, right? The general solution is always going to come first. Remember, parentheses, yes,
I
question?
keep getting 6. I put in the calculator and I'm not getting 25.
Okay, I'll help you after class. So we're going to make sure the parentheses is there in place. It's not going to, we don't want to lose the parentheses. So let's divide by 1 here. Get that diagonal to show up for us. Okay, cross multiply. Okay, we get that dy dx showing. And that's good. We know that's not gonna change, that's in the right spots. But what is out of place? Is there anything out of place? Yeah, that y. And that parentheses is helpful because if I want to move the y, everything inside the parentheses has to go along with it. Okay, so I have 1 over y minus 1 dy equals integral of x squared dx. Okay, we have full separation of variables. It's okay to have variables in the denominator. Now this left side is a simple u substitution with the u value being y minus 1. Will that produce any derivative other than 1? No, right? So it should just end up being 1 over u. And we know 1 over u, we can use what? Yeah, yeah, natural log. Okay, so the left side is natural log. You know that 1 over u is natural log absolute value of u. Replace the u back in terms of the original variable. And the right side is just what? Power rule, right?
X cubed
Yeah.
over 3. 1 x.
And then plus c. Okay, we have the general equation showing, but now we can get to the y. Well, we have the equation showing. How can we get to the y here? Yeah, raise both sides. E is the base. Left side drops down. The right side we can split. Remember that plus c doesn't stay plus c. It turns into a multiplication. Yep. We know e to the c is just c. Drop the absolute value. This is the general solution. And how can I update the general to the specific? Plug in the order pair, right? 0 in for x, 3 in for y. E to the 0 is 1. Okay, we'll pick up tomorrow.
And that's right on the top of my head. And it was a perfect pass setter. Better than if I got my hands up. But I was literally just standing there. I didn't even see it. It just, I didn't even move my hands. I got my hands up. It didn't even hurt. It just felt like a ball.
I should be able to. Because that's 5. Right. So I need to really pull out the negative 3 here.
Yeah, I just ended up leaving the 2 blank curve buttons.
Okay, appreciate it. Thank you.
Also, I ran out of green ink.
Okay.
I just tried to use it.
That's fine.
I
I'll
got
bring it
it.
tomorrow. You got it?
Yeah.
Okay, good. Got it.
Did we get a worksheet for 5.7? Because I didn't see it in the packet.
Oh, it should be in the packet.
Is it not? Is it in the packet? I didn't look all the way through.
Yeah, let's see.
So, yeah.
Good day.
It's probably in the middle or something.
Yeah, it's page 23.
Oh, awesome. I definitely. Okay, thank you. I just did this here.
Okay. I'll look at it. I appreciate it.
I was just really quick to say, how do you do LN on the calculator? I forgot.
Right here.
Oh.
There you go.
Thank you.
I'm not going to be Friday, so I just figured it up next week.
Okay, sounds good.